You're actually using it at this very moment. In fact, you've probably used it a dozen times today and didn't even think about it. I'm talking about encryption.
And in this explainer, we are going to pull back the curtain on the one fundamental secret that makes our entire digital world possible and, keeps it private.
But before we dive in, let's just start with a quick thought experiment. What if every single message you sent, your texts, your private emails, even your banking password, was written on the back of a postcard just out in the open for anyone to see?
Right. The mail carrier, the person at the sorting office, literally anyone could read your most private thoughts. Sounds like a nightmare, doesn't it?
Well, without encryption, that's exactly what the internet would be.
So let's really lean into that postcard idea for a minute. Because to truly appreciate how brilliant the solution of encryption is, you have to get your head around the massive scale of the problem it's trying to solve.
And this slide here breaks it down just perfectly. Over on the left, you've got the open postcard. This is your data, traveling in the clear. Every single person who handles it, every router, every server, can take a peek inside. But on the right, that's the goal, the locked box. Now, the box itself travels the exact same route, but what's inside is a total secret. And this really gets to the most critical idea of all. Encryption doesn't hide the package, it hides the meaning inside the package.
And you absolutely need that locked box because of this. Just look at the journey your data takes. It's not some private, dedicated tube from you to your bank. No, it's a crazy, chaotic web of shared equipment.
The second you hit send, you've completely lost physical control. And at any one of those stops along the way, someone could just, make a copy of your message as it flies past. It's that easy.
Which brings us to a really radical, almost uncomfortable truth at the very heart of cybersecurity. We have to just accept that we can't always stop attackers from getting their hands on our data.
Whoa, okay, hold on. So you're saying the game isn't about building a bigger, stronger wall?
Exactly. The game is about making sure that when they finally get over the wall and break into the vault, all they find is a box of worthless, meaningless rocks.
So, how in the world do you turn treasure into a pile of rocks? Well, that is the magic trick, isn't it? It's the core of encryption. You don't hide the data itself, you hide its meaning. And you do that by completely destroying its patterns until it looks like pure chaos.
Now, to really wrap our heads around this, we have to split one concept into two very different things, semantics versus representation. Okay, so semantics is the meaning, the pure idea of the number 2. Representation is just the symbol we use, like the digit 2 or the word 2.
And we get meaning because we recognize the patterns in that representation. So the entire job of encryption is to be a pattern-destroying machine.
Exactly right. Look at this plain text on the screen. This is a secret. Your brain understands it instantly because it's just loaded with patterns we recognize. The double S, the spaces, the shapes of the letters. These patterns are the doorway to its meaning. But now, look at this. These are the exact same letters, just scrambled up into what we call ciphertext. All the information is technically still there, but the patterns, they're gone. It's just meaningless noise. And that is the fundamental goal. Transform a clear signal into random noise for anyone who doesn't have the secret key. So, to put it as simply as possible, the process takes something that makes sense, the plain text, it uses a secret key, and what comes out the other side looks like complete and utter random chaos to anybody who's not supposed to see it. Okay, I think I'm getting it. So, can we see an early version of this in action? Let's do it. Let's travel back in time, about 2,000 years, to one of the very first stabs at this whole pattern destruction thing, the Caesar Cipher, which Julius Caesar himself used for his military messages. The method is actually beautiful in its simplicity. So first, you and your friend agree on a secret key, which in this case is just a number. Let's pick 3. Then you take your message, your plain text, which is hello. For every single letter, you just shift it forward 3 spots in the alphabet.
Oh, I see.
So H becomes K, E becomes H, and so on. And just like that, hello turns into KHOOR. Okay, that seems easy enough. So why is this considered so weak? Why is it so easy to break? Well, there are 2 huge reasons. First, an attacker only has to try, 25 different keys to guess the right one? A computer can do that in a blink. But the real fatal flaw is in the patterns. See how the double L in hello becomes a double O in call a war? The pattern is still there. And it also says here it's vulnerable to something called frequency analysis. What's that? Well, that's just knowing that E is the most common letter in English, followed by T, and so on. An attacker just counts the letters in the scrambled message,
finds the most common one, assumes it's probably an E, and cracks the whole thing in minutes. The ghost of the original pattern is still haunting the message. You know, the failure of the Caesar cipher taught cryptographers a really important lesson. Any predictable relationship between the plain text and the ciphertext is a major, major weakness.
And that realization sent them on a quest for the Holy Grail, a truly mathematically unbreakable code. And believe it or not, they actually found it. It's called the One-Time Pad.
The classic way to think about this is the twin notebooks analogy. Picture two spies. Each of them is given an identical notebook filled with pages of completely random letters or numbers. To send a message, the first spy takes their plain text, combines it with the random stuff from page 1, and sends the scrambled result.
And here's the crucial part. They both immediately burn that page. It's used one time and only one time ever. The resulting ciphertext is provably perfectly random.
Now, in the digital world, that combining is done with this elegant little piece of logic called XOR, which stands for exclusive OR. The rule is so simple. If the two bits you're looking at are different, the output is a 1. If they're the same, the output is a 0.
And the magic of XOR is that it's perfectly reversible. If you take that scrambled result and XOR it with the exact same key again, you get your original message back, perfectly. It's like a secret light switch.
Okay, let's actually see this happen. First, here's our original message, our plain text, written out in binary. Next up, we need our key. And for the one-time pad, this has to be a truly random string of bits that's the exact same length as our message.
All right, now we just apply that XOR rule bit by bit. 1 and 0 are different, so we get a 1. 0 and 1 are different, so that's another 1. 0 and 0 are the same, so that's a 0. We just do that all the way down the line, and this is what we end up with. And just look at that. It is mathematically indistinguishable from a random string of numbers. There is absolutely zero statistical connection back to the original message. This is perfect, unbreakable encryption.
Okay, wait, if this is perfect and unbreakable, why aren't we using it for everything? Why isn't my online banking using this right now?
Well, it all comes down to a huge clash between perfect security and day-to-day practicality. I mean, to encrypt a 1 gigabyte movie, you need a 1 gigabyte random key. But the even bigger problem is this. How do you get that giant key to your friends securely in the first place? If you already have a secure way to share the key, why not just use that to share the movie? It becomes a total logistical nightmare.
Okay, wow, we have covered a lot of ground, from ancient Rome to modern logic. Let's boil this all down to the absolute key takeaways. All right, takeaway number 1. Remember that our digital messages are basically open postcards, and encryption is the locked box that protects them. Number 2. That lock works by destroying patterns to hide meaning. And we saw how simple codes like the Caesar cipher fail because they leave behind clues, those ghosts of the original patterns. And finally, perfect pattern destruction is actually possible with something like the one-time pad, but it's just way too impractical for everyday use.
And look, if there is only one single idea that you take away from all of this, please make it this one right here. Encryption protects meaning, not access. The goal isn't to build an impenetrable wall. It's to make sure that anyone who manages to climb that wall finds nothing but a box of gibberish. Which, of course, leaves us with a giant, fascinating question. If the only truly perfect encryption is completely impractical, how on earth does the entire modern internet function securely every single day?
Well, that is the magic of modern cryptography. And it's a story for another explainer. Thanks so much for joining us.